Very good morning, dear participants and distinguished speakers. I welcome you all for the day 3 of the program on computer-assisted design and manufacturing in clinical diagnostics and therapeutics, supported by All India Council for Technical Education. Without further ado, let's go on to the first session. The first session for today is Advanced Modeling Tools for Biomedical Applications 3D Printing by Dr. Y. Ravi Kumar. Dr. Ravi Kumar did his BTech in Mechanical Engineering from JNTU, Kakinada, ME in Computer Integrated Manufacturing from PSG College of Technology, Coimbatore. He did his PhD in Mechanical Engineering from Osmania University, Hyderabad, and postdoctoral research in 3D printing at Milwaukee School of Engineering, United States of America. He is now currently working as the Associate Professor in Mechanical Engineering Department, National Institute of Technology, Warangal. Kindly take over, sir.
Yeah, very good morning, one and all. First of all, let me thank the organizers given me this opportunity, Dr. R. Arun Kumar and his team members, and the management of Chitnadu group of institutions, and of course ACT Atal scheme. Let me share my screen first of all. Can you be confirmed, madam? Is my screen?
Yes, sir. We are not able to see now.
Okay. Yeah, 1 minute. Yeah, is it okay now, madam?
Yes, sir. We can see now, sir.
Okay. Let me go to the full slide mode. Can you please confirm the screen, the status
yes,
of the
sir,
screen?
we are able to see, sir. Clear,
Okay,
sir.
Thank you. Yeah, very good. Good morning, one and all. So, and thank you for the opportunity to talk before you. And this talk will be on advanced modeling tools for biomedical applications of 3D printing. I hope this is the third day of the program. By this time, you might have already exposed to various tools, CAD tools and CAD-CAM tools for medical applications. And my talk will be, of course, the theme of the workshop is also revolving around 3D printing technology. And I have organized my talk in this way, where you can see the list of contents. So this session primarily focusing on to the advanced tools for medical application of 3D printing. Means basically, how do you generate the CAD tools, or rather than the format that the 3D printing is readily to take from the any medical image processing software. Basically, during this talk, I will be focusing on to the tools and the modeling aspect of these medical application of 3D printing, and we have another session, so that will be focusing on the surgical case studies. And during this talk, let us quickly introduced this 3D printing technology. And the start point of this 3D printing technology in medical application, undoubtedly, we should start with the medical image data processing. That is where you will be starting your journey with the images that has been acquired from the patient, either through a CT or a MRI or ultrasound, or even it could be an X-ray, digital X-ray. So then we'll be spending some time on how do we process this data, and that will be ready for the 3D printing application. And though we have several modeling tools and the softwares and the packages, but still, why you are looking for the physical model, the importance of the physical model in medical applications, that also will emphasize on. And of course, reverse engineering tools is the another set of tools that will be oftenly used in medical applications, but predominantly used maybe CT, MRI, the data acquiring through a CT, MRI, or the allied, say, the modalities. But even reverse engineering is also used in medical practitioners, but oftenly you may be using it. Then we will see the reverse engineering tools that are available for medical applications, and how do you develop your medical application. So then that also we are going to see that how do you develop a medical application using 3D printing technology. And we will be spending a little bit of time on the data format. Why? Because without knowing this data format, so you cannot work on any 3D printing technology. So then we'll focus on a data format. And of course, the topology optimization is gaining a lot of attention, and the bionic designs. And it is quite important for medical applications also. You may have other applications like aerospace engineering applications, but even the medical applications also, your bionic designs are playing a vital role. And then we'll see various tools are available that to optimize the topology or designing by inspiring the biology of the it may be through a cell biology, or maybe it may be through a sort of, say, some lattice structures, or some, say, some bio-inspired designs that will see how these designs and 3D printing are getting connected. And we'll see some of the simulation tools that are available for 3D printing. And though this technology is doing relatively good, but we do have certain challenges to fabricate these 3D printed models. But then that comes to medical application, then we need to have other challenges that we should address. So this is what I have planned for the next 1.5 hour. Say, then let us get started this session by introducing this, first of all, the 3D printing technology. And probably you may be coming across the different names, say, right from the rapid prototyping. So rapid prototyping was the former name of this 3D printing technology, where it was started in late 80s and early 90s. So where it was a tool for a designer to validate the prototypes. quickly or rapidly producing prototypes. So that was the technology coined by Chuck Hull during late 80s or early 90s. And then this technology has been renamed with other names like additive manufacturing, 3D printing. You name this technology, either you name this as a rapid prototyping where your scope of application may be limited to prototyping applications, but if you call this technology as additive manufacturing, the scope is enhanced, so it may be the fabrication technique or the manufacturing technology, the additive in nature. Um, and of course, 3D printing is a common name, as we say everybody knows the printing technology means either a laser jet printer or an inkjet printer, basically which prints in 2 dimension. But whereas 3 dimensional printing, where you have the third dimension, right? So the essence of this technology basically is we need to start your journey by a digital model or a CAD model or a virtual model. So that is going to be the start point of your journey. So that digital data, it may come from an engineering product like a car or a aircraft, or even it could be a consumer product. Typically you start right from the scratch, means by adopting some CAD CAM tools or the softwares or the packages to model your product, say right from the scratch. So that is one way of starting your journey. Or even we do come across reverse engineering. Say you have a physical object, you have a physical product which it has been already existed, means somebody has sculpted or somebody has say say fabricated some physical say car body, a typical example. So then which we need to digitize them. So
conventional surgery, we have to expose the bone. For example, the knee joint or the joint, we have to expose the bone to see and feel the bony parts inside. So the major incision is used. So there is always a saying, big surgeons use big incisions. But with the advent of computer-aided surgeries, we do minimally invasive because my probe is going to feel the joint parts. I don't have to see. If I put the probe, it will locate where I am. So it is minimally invasive. What is the advantage of this? It prevents bed loss. There is less soft tissue damage. Because of this, the post-operative rehabilitation or the mobilization of the patient is faster with less pain. And in fracture trauma surgeries, particularly involving the articular surfaces where accurate reduction is necessary, we can go in for computer-aided surgeries where we can accurately reduce the joint for better range of motion for the patient after trauma. Another base advantage is we don't have to use the C-arm radiation, which we have been using constantly. We don't have any radiation exposure to the patient as well as the surgeon. And whereas the active applications, particularly in the hip and the pelvic fractures, which are deep-seated joints in the body and major joints in the body, surrounded by important blood vessels, neurovascular structures, as well as the liver, spleen, kidney, gallbladder, which are very close to the spine. We use this the trajectory navigation, the spine surgeries or tumor biopsies, pedicle screw placements. And in intra-articular fractures, it is used to assess the accuracy of your joint reduction about the fracture. And in navigation orthoplasty, where it helps the surgeon in accurately placing the implants for better function of the joints. And the other few uses where mostly it is for osteotomies and the ACL ligament reconstruction procedures, and as a training tool for young surgeons in the form of simulation, and the patient-specific implants where we can design with particular, where the patient is abnormal anatomy or bone defects are there. So conventional implants may not hold, we can design specifically for those patients. And CAD-CAM extensively discussed for the last few days. And I'll be mainly dealing with only designing of the 3D data which of the patient and where we use for surgery. Mainly how we go about navigation surgery. Basically, these are the three units: a computer unit, a tracking unit, and a tracking mounted hardware. So this is the computer unit, which is like a normal CPU, which receives data from my operating field, my hand tool, everything has sensors in it, and the C-arm machine, and all these data are processed, and a virtual model of the bone of the operative area can be reconstructed. Next, this is another second position sensor, which is called the third eye of the surgeon, or the God's eye we call generally, because it watches my surgery throughout the procedure, and it gives me feedbacks where I am, how much bone I am cutting, what is the angle I am going, everything. So this is the second important point. And these are the sensor tools which are placed on the operative field, actually on the bone of the patient which is going to be operated upon. So these are the three elements which are very important for performing my surgery. And probably for tracking, we use these two common: optical tracking and magnetic tracking. Optical tracking is, we are all used to mostly optical tracking because it is like a video game play. So we are used to it. And magnetic tracking has certain advantages over optical tracking, but because it doesn't use these sensors and the surgeon can freely move around the operating table without obstructing the view of the optical sensors. But and it is device, it is a special operating table, which everybody cannot afford. And these are my smart instruments. These are the customized orthopedic implants. You can see the three white beads. These are the optical sensors which can be fitted with every hand tool in the surgical, either it is in the jigs or in the cutting saws or in the drill machines or in the arthroscopic cannulas, wherever. So this gives the data to the through the optical sensor to the computer. So this is used, and you can see always there are minimum of 3 sensors being used, because this gives a better spatial orientation and the 3-dimensional configuration. More the number of these optical beats, more the accuracy of our image which is created. Next, this is called triangulation, where always this is a hip which is operated upon. I use the fixed tracker on the hip or in the knee, wherever I'm getting operated. This is a fixed tracker. This is a surgeon handheld instrument with the tracker. So this is seen by the third eye, which is the optical localizer. And whatever I am moving or doing is visualized and fed to the computer data, which gives me a feedback in the virtual model. And how do we go about? We first do the registration. Registration is nothing but feeding the bony landmarks of that particular area which is going to be operated upon. With the help of optical trackers, that data is fed. And through the optical sensor, it is fed to the computer, then which creates visualization is nothing but creation of the 3D model or the virtual model of the bone, which we are going to operate. And validation is nothing but correlating the image which is generated, whether it is matching with the actual patient data, anatomy, which we are going to operate. This validation this is a constant check process where we have to keep validating constantly throughout the surgery, and particularly in the important steps of surgery like implantation or cementation in a joint, we have to keep validating continuously so that the actual model which is generated is replicating with the actual anatomy of the patient. Commonly, these are the systems which are used. The CT, ultrasound, the MRI-based navigation was used in the past. I'll just see how it has. I'll just show you how it evolved. Now, constantly, we are using this passive navigation system, which is CT-free, radiation-free. And these I'll discuss in the corresponding slides. This is what it started with, which is basically a 2D navigation. It is actually, it is only a templating. It is not a navigation per rock. What we do is we can get a CT picture of the patient. And before performing the hip surgery, I want to know what will be the socket size, what is the inclination of the implant which I have to use. And basically, I can just see this, but this will not match in the post-operative, perioperative scenario, because this may change. I have to order for 2-3 sizes extra, because on-ground reality may be different. I don't get any help on the table. And another thing on the hip side, this is called the templating, where I have superimposed an image of the implant which can be used, and I can get data whether this will fit, whether it will fit in the canal properly in the more depth views. This is just to guide the rough guide for the surgeon. It will not help in the actual performance of the surgery. The implant sizes may differ, the positioning may differ. This is just to get an idea of what size will fit in this particular patient. So after that, we evolved to this better with the advent of 3D image data. We can perform the surgery on a virtual model, and I am now checking. This is a patient with a hip replaced implant. I am checking whether this implant, the patient is now standing. Everything looks fine. But once the patient is made to sit, you can see a red danger mark. What that means here is, this particular implant, once the patient is going to sit, particularly in a car or where he's going to flex the hip, this can impinge. And what can happen is this process may dislocate. So it is giving me an idea preoperatively that I have to change lightly the version of this hip implant so that this impingement is avoided. So this was the next evolvement, that we could get the information before performing the surgery. Now, what computer navigation does to me by performing my surgery, this is actual surgery of hip. This is the head end, this is the feet end. I am trying to fix a fracture neck femur here. So as I told you, this is a fixed array on the pelvis, and this is a surgeon's hand placing the drill guide. So now this is the neck femur fracture in the hip bone, which I am going to fix. I am getting all the data. See, this fracture is best fixed in a what we call the triangular configuration, where the apex is here. It is in the triangular configuration. So minimum 3 screws to be used. With just placing the drill guide on the bone, I can get the trajectory. You can see, notice the length, 96 mm of the screw. And not only that, for placement of the 3 screw within the neck, if I have to use a 4 mm or 4.5 mm screws, these are the data which will help me actually in performing the surgery more accurately and with accurate placement of the implants. That is the advantage compared to a 2D navigation. And previously we were used to all these. This is a normal radio CM plate, base plate, which receives the X-rays. And you can see the white beads, which are the radio opaque element. We were using this previously before computer navigation. This is what we used to obtain. This is spine surgery in progress, where you can apply data in the 2 views only. And these dots, radio opaque markers, give me that area where I have to put my screws. This is the pedicle here, and where I have to. This is the way we were going about. This is only it is only restricting you to a 2D navigation. But with the advent of computer guidance, we are able to get multiple images. Not only that, the moment I put my probe on the pedicle, it is giving me a direction where this screw projection will be, and on all the planes. I have to just tilt my handle to know which direction I have to go and what is the screw length, what is the trajectory, everything I get in one go. So this is a post-op X-ray of the patient for a fracture he has been operated upon, where you can see the adequate placement, everything, screw length, everything is perfectly reconstructed. So this is the advantage I need during operation. And this is a 3D navigation and CM navigation, which involves radiation, which was used previously. So what we get is on all the axial, sagittal, coronal planes, we get the images, and we are fixing the fracture around the knee. This is the proximal tibia fracture being fixed. And we can get the screw length, as well as we don't go intra-articularly. The screw should not penetrate the joint, and the articular surface has to be reduced accurately for post-operative functioning of the joint, because the movement of the joint depends on adequate reduction of the fracture. And coming to the real part, talk of the today, where we use computers for knee app. This is my domain. I'm an orthoplasty surgeon. Commonly, we use computer navigations. Basically, we use the passive navigation system without the CM radiation. And CT-based navigation is going out of vogue now with the advent of computer navigation. And robotic is still in the evolving model. For the benefit of the non-medical people, what I'll be talking about. So this is basically a normal knee lined beautifully by a cartilage. This cartilage is like a highly polished porcelain or a ceramic, which doesn't have any nerve supply or a blood supply of its bone. It derives its nourishment from the synovial fluid, in which it is bathed. So that is why when we run, when we jog, when we do all twisting, dancing, we don't have any pain in the knee. But what happens once the cartilage gets worn out? The subchondral bone gets exposed, and the patient develops, because the subchondral bone is rich in its nerve supply, it starts with pain, it starts with stiffness, it starts with deformity, all these start. That is called arthritis. So this is the X-ray picture showing what is normal. Beautifully, the joint space is maintained because the cartilage is intact here. What happens in arthritis? The bone ends starts rubbing against each other, deformity starts, and patient develops pain and difficulty in walking. So with this, what is normal and abnormal, we go what we are going to achieve. So these are the clinical scenarios we come across commonly in the knee. This is just simple two-plane deformity. We receive more other deformity in tibial torsion, everything in clinical scenario. But to make it simple, this is called the bow knee deformity. This is the knock knee deformity. And I bring your attention to this slide, which is normal. Don't bother about all the lines. Just remember this red line, what is called the mechanical axis of the lower leg when the patient is walking. The center of the hip, the center of the knee, and center of the ankle. Even though the Anatomical axis of the bone is different. While walking, this restoration is necessary. This is called the mechanical axis of the lower limb. What happens when the patient has a deformity like this? You can see the red line. It is miles moving away from the joint. Not only that, you can see this line. In normal, it is parallel to the floor. That is why we are able to walk normally. Whereas once this deformity starts, this angle also changes. The parallelity between the floor of the knee axis also changes. So the patient finds it difficult to walk. And this is a bow leg deformity where the mechanical axis falls inside, on the inner side to the knee. And this axis is also changed. So what we do, what we want to achieve in a joint replacement in the lower limb is restoration of this axis. That is, more accurately we restore this axis, we get a better joint function in the long run. So how do I do it? As I told you, we have placed this is the knee replacement in progress, where we have placed the trackers in the thigh bone and the leg bone, and my third eye is ready for helping me. And what I have to do, as I told you, registration is the first. We have to spend some time in registering these points. Now I'm moving the hip, patient's hip on the table. Then the computer visualizes and generates the data of the center of the hip, then the knee, then the ankle. So it is given what is the axis of the hip, what is the axis of the knee, and what is the ankle. It generates a image. Next, I have to give the bony landmarks of the thigh bone, and here is the leg bone and the ankle. So I give the various bony landmarks for the computer to generate a accurate 3D model for this particular patient. There may be defects for the patient depending upon the wear out. Everything will be accurately replicated in the computer generated model. This is called registration process. Then the computer, after giving everything, the computer generates what is the preoperative axis before implantation, and what if the patient has a flexion deformity, will show how much, about 30 degrees, is not able to fully extend. Now here this patient doesn't have a deformity, so it's showing like, so this is what it is giving me, the mechanical axis. Now I proceed with my surgery. So here I am using the probe for the distal femur cut. I'm preparing it, how much of bone to be cut. So moment I keep this, the computer can give me the guidance about what is the angle to be cut, how much of bone to be removed, and all these again. This is the distal femoral cut in the thigh bone where we cut. So this is giving me, computer is giving me a data. The moment I place the probe, this is the saw through which I will place my saw to cut the bone. It is giving me 9 mm. 9 mm is the minimal cut necessary because the implant thickness is commonly 9 mm. So this data I can get through the because of the virtual model generator. Then I proceed with my distal femoral cut. Next, coming to the next tibial cut. After I cut the femur, I am going to the leg bone, which articulates, that forms the knee. So this is, the jigs are placed and the trackers guide me how much I am cutting. Again, 9 mm. And 9 mm is the implant size. So minimum is 9 mm. I can cut less. If the defect is more, I will cut less. So this is giving me the slope, everything in one dimension. After that, I cut this thing, proximal tibia. Then we have to see, after these cuts, we have to see whether how the knee is stabilized by its ligaments. It is not just placing the prosthesis accurately and coming out. If the ligament is not balanced, my knee is going to wobble. So I have to check the ligament balancing after these two cuts. One in flexion, this is in flexion, and in extension, whether the joint is stable. After that, I proceed with my further cuts. So once I implant, after that I implant. This is the post-operative X-ray showing the restoration of the mechanical axis, which is passing from the center of the hip, center of the knee to the center of the ankle. And you can see the implant in place. This is the final picture in the computer where I have replicated what I wanted. And the X-ray is confirming that the surgery has gone as per what is the planning. So this is the advantage of navigation procedures in a orthopedic surgery. And next we do other common surgery where I navigate is the ACL. You all heard of sports person undergoing this arthroscopic reconstructions. For the benefit of the non-medical people, what is these two ligaments, there are two ligaments which are the intra-articular stabilizers of the knee, which doesn't allow the knee to buckle in whatever movement we do. For a sports person, this is very, very important so that he can perform better. And once this ligament is torn, commonly in footballers, contact sports like kabaddi or footballers, they cannot play further because of the instability. So we have to reconstruct this knee. How do we reconstruct this? Taking a patient's native ligaments like like the hamstring tendons, and we reconstruct. Why navigation is necessary is accurate placement of the graft is necessary for the function in the long run, so that the sports person can go back to sports. So this is the ACL navigation in progress. Same way, after registering all the bony landmarks, we get an image in the computer. And I am placing the probe now. So it is showing where it is. You can correlate it either arthroscopy or this generated model. First and foremost is I reconstruct see the notch, what is the notch topography of this patient, because some patients will have wide notch which can accommodate a larger size graft. Some patients may have a narrow notch which can impinge. So I have to know this. Then this is what computer aided surgery gives to me. Previously, by arthroscopy alone, I have only less reference landmark by placing my tunnel. This is in the tunnel in the tibial bone, where the computer takes multiple references. See, it can take from the lateral meniscus, from the PCL, from the tibial eminence. Then it projects what is the best possible tunnel fixation for this patient. So I'm guided in that way. And coming to the next, the femoral tunnel preparation, along with the notch, it gives me with various references, it gives me where will be my tunnel in the femur bone. Now you can see everything is green. Here there is a red mark. This red mark indicates that for that particular size, I have to watch for an impingement of the graft there. So I have to, performing the surgery, I have to watch this area. This is about 12 o'clock position. You can say about 9, 10 o'clock position. I have to watch whether it will impinge or not. This is what is the beauty while performing the surgery. We can actually move the knee joint on the table and assess the laxity for this patient. It is giving me, see on the lateral side, outer side, it is moving more. About 13 mm laxity is there. On the inner side, it is showing me only 5 mm laxity, and also on the rotation. So where inner rotation, outer, every data we have, so that how much we have to correct for this particular patient. And it is documented. Previously, we used to say grade 1, grade 2, and depending on, it is all, error can happen in patient surgical, in intraoperative surgeon's assessment. But here I have a data. After that, I decide where I go to place my tunnel, and it is generated on the tibial model and the femur model. Now, this is what is the red mark shows for this particular size graft. This is the ACL graft on a virtual model before actually putting the graft. If I put the graft and I extend the knee, this can impinge there. So what I do, I have to either put a smaller size graft, or I have to change the tunnel slightly, either on the femur or on the tibial side, to adjust the graft size, or I can do a notch plasty here so that it doesn't impinge. These are the ideas which I get on table. And for some surgeons who are not very extensive in using this computer navigations, for a quick surgeon, he just uses a simple fluoroscopy, places the probe, and goes about with this. This is a simple 2D navigation without much paraphernalia. He just goes on to place the graft. And here I am getting my arthroscopic picture as well as the image picture, which is generated by the computer model. So I am placing the probe here inside the tunnel, and it's showing, once the moment this is a probe, with the black color is a probe, it is showing the trajectory where the bone, in the femur bone as well as in the thigh bone. And once the graft is placed, I can see whether it is matching the trajectory what I have decided. Next, we have finished with the knee. Then we are coming to the hip replacement, where as the fixed bony points are placed in these 2 points in the iliac bone and the pubic symphysis, which is shown here. And after that, I start, after registering again the hip axis, knee axis, and ankle, all this. I go about, the computer is going to guide me regarding the acetabular shell. The hip joint is a ball and socket joint, as we all know. I am now placing the socket of the hip through the navigation. What I do, the computer generated model gives me what is the inclination, what way I cannot place my cup vertically or horizontally for fear of post-operative dislocation. If it is not accurately placed, the hip can dislocate or it can wear out in the long run. So it is giving me what is my inclination. I just have to move the handle to show what is the inclination. I don't have to do a wide incision to see the bony landmarks and then place my cup. See, the incision is small, but I can see on a computer which is the two things which I see is the inclination and the anteversion, which is very important. That is shown here. After that, I impact my cup. Here, I am getting the data. Normally, this is a normal version of the cup, which is 45 degrees, which is normal, and the anteversion is about 13 degrees here. We can go up to 15, 20, which is normal anatomy of in the normal anatomy, we have this dimensions. So it is giving me an idea, and I impact the cup. And then coming to the femoral side now. Once the socket is placed, I come to the femoral side. Now the computer is guiding me where I have to open up the medullary canal. And this is what we mean by version. Version is just the head and neck axis is placed at about 15 degrees normal to the axis of the thigh bone. So that data I am getting. And I can template on the operative field. I can template a known implant design and try to fit in which implant can go it to me. This advantage I have. I don't have to do a trialing in the actual bone. So I just see. Then not only that, another important data which I get, if I fit this implant, where will be my center of rotation of the hip? And it is showing if I fit, I may have a leg length discrepancy. This is what is important for me. If so, I have to use a different implant where I can correct the center of gravity as well as I have to correct the leg length, so that I use a smaller diameter prosthesis, or I change the offset in the head neck so that both limbs are accommodated, so that the leg length, there is no leg length discrepancy also. This data is very important post-operatively. Otherwise, the leg length of 4 centimeters is going to cause a patient to walk in a wobbly manner. And here it is showing the sizes, what sizes I have to broach, that is to open up the canal here. All these data I am getting. And then we perform the hip replacement. This is a highly technical operation where this is a resurfacing arthroplasty. Unlike a hip replacement where I violate the medullary canal here and put the stem. This is an unforgiving operation where we have to accurately place the neck on the socket, because we don't violate the intramedullary canal, and it is mostly done in young patients with arthritis who may need a future joint replacement, who may need a revision because it is done in a very young age. So again, after the registration, the bony points is in progress, and the computer has generated me a model. I am validating whether the point where I place is corresponding with the bony model. And then this is actual navigation. I try to place a known template, a known implant size, and it is giving me what is the neck shaft angle, 130 degree here. What will be the version? Now it is showing retroversion here, which I have to correct into anteversion. What will be my size of the implant? All these I get data based on that. Then I finally go into and impact the shell. This is after the surgery. Previously, we used to only get this data, X-ray templating, which will not help me in performing actual performance of the surgery. For example, in the same patient, when we have done an X-ray templating, the size is showing about 36 or 38 here, which I have written. Whereas during navigation, the size has changed. It is about 46 it's showing. And what is the stem planning, everything. So it is a final, after finding final X-ray picture of the patient where we used a 46 cup on the shell. And this is unlike a total hip replacement. We don't violate the canal here, which will be available for me for a future revision in a young patient. And after arthroplasty, the next common surgeries where we use computer models are this high tibial osteotomy. This is a procedure which is done when there is a unilateral arthritis where only one compartment is involved. The patient need not undergo a major procedure like a total joint replacement, where we just change the axis to restore the mechanical axis. We just cut the part of the bone and close the wedge, and we get the mechanical axis right. This is called high tibial osteotomy, commonly which is performed for unilateral conditions where only one part of the joint is involved in arthritis. So this is operation in progress. We have just opened the lateral outer compartment of the leg, and after this is a tracker on the leg bone, feeding the data, registering the data. After that, I get an image. This is a saw capture, how much I have to cut. I am drilling with the help of, I have to just put my saw, which is along this, wherever I have planned my osteotomy. So here it is showing the actual saw, which we are cutting on the bone. I did not see the other side. I did not open the other side. I just have to go in. So this is a final 3D model which is generated, and I can see in all the planes. I can rotate this and then see. And this, after removing the wedge, this is the mechanical axis of the patient which was previously before surgery, and this is what I want to correct. So moment I close this osteotomy here, you can see this, moment I close this osteotomy here, this axis which is previously will come and merge into this, so that what is my desired mechanical axis I'll get. So that type of accuracy we can take in the bone. And this is the pre-operative X-ray showing where we have proposed a cut. And this is the same patient post-operative after we have fixed it with staples. This is the opening of the inner surface. You can make it was narrowed here and it is opened out here. Next, in spine surgeries, commonly these three surgeries we used: pedicle screws, scoliosis correction, and tumor surgeries. Again, a spine surgery in progress where we have put the fixer tracker on the spinous process, and the surgeon's handheld instrument probe is pointing the entry point for the screw. So with this, and not only the screw placement, we can get the screw. Actually, we can drive the screw inside using the help of these trackers. That is what we are doing here. Moment I put a probe, I can see the green line is a simulated length, which the computer is showing me where to go accurately, whether I am inside the pedicle, this is the pedicle, I am inside the pedicle, and where direction I have to go. All these I get without the danger of crossing the canal or damaging the spinal cord or the nerve root. And next is scoliosis. We see this crooked deformity of the spine, where the young adolescent female comes with this type of curvatures in the spine. They want it to be corrected. And at the 3D model, we can know now we have generated where we have to place our vertebroplasty. We have to cut this much of bone in the vertebral body to correct the spine to a reasonable angle. So we generated this. And this is a post-op picture showing correction on the screws placement, almost restored to cosmetically better function for this patient, better correction for this patient in both the angles. So this is what we can achieve if we are navigating. Another thing is in tumor surgeries of the spine, because spine is surrounded by a lot of important soft tissues in the form of spinal cord and other vertebrae, aorta and the inferior vena cava, the blood vessels which are there in front of the body. And the tumor, we don't know that we can't assess the exact tumor size, even on surgery at times. We use, for taking biopsy in these lesions, we take the help of navigation, which we can do with minimally invasive, without opening much. This is a sort of L5 vertebra body tumor. This may be a cancerous lesion, the way it looks like. So I want to know what is this lesion, how to and do a patient probe, and I have to go. And I bring it to your attention, this is the aorta, which is so close to the vertebral body. Hello? Hello, am I audible?
Yes, sir.
Because it's some internet instability is showing to me.
It got stuck. It got stuck for like 10 seconds, sir, but it is okay now, sir.
Yeah, please tell me if I am stuck. Just tell me, yeah. Okay.
Sure, sir. Sure.
Because I don't know have any reaction from that side. So, okay, this is the vertebral body which is cancerous. See how close is the aorta. This is an elderly patient having calcified aorta. How close is this to the bone? So any degree of error is going to puncture this aorta and land up in complications. So with this navigation, I know where I have to go in, and the trajectory it is going to give me the exact idea where I have to take in a biopsy from a representative type, and we can safely play without opening or without anesthetizing these patients who have already plenty of medical problems. Now in trauma surgeries, basically we need to do in intra-articular fractures where it requires high accurate reduction of the intra-articular fragments for better function of the patient. This is a pelvic trauma where the surgery is being done for fixation of the sacroiliac screw. This is the sacral bone, and this is the pelvic bone where we try to reduce this and fix the screw. See, now I can do this percutaneously. Moment I put the probe on the patient, I can see the trajectory and I can see how safe it is, because anteriorly the bladder, uterus, vessels are there. Posteriorly the spinal cord comes here. So I have to avoid all these structures, and it is showing me very beautifully in these two views where I have to go in. Not only that, you can see the markings here. About 90 mm of screw is necessary, 90 to 100, and 3.5 to 4 mm is the diameter of the screw which you can place here. So this is accuracy which you can get when I try to do with computer navigation. And this is in trauma surgeries, when the leg bone, this is the leg bone. I am getting the trajectory, how to enter the medullary canal inside, so that I can put a proper nail has been placed, and the locking screw for getting the locking screw, I can use a simple X-ray and then lock the screws. And this is what computers me. I can do this is a hip fracture in progress. I have to fix after reduction of the hip fracture. There's a trochanteric fracture here. After reduction, I can just put template the implant over this on table on a virtual reality, and then assess what will be the screw length, what position I have to go, where I have to put my drill entry, everything I get. With that, I can easily reduce my fracture. And this is in fracture reduction. This is the lower limb, leg bone fracture. The proximal green part is the proximal part of the bone. This is the fracture. The red is showing the distal part. This is showing after reduction. Once I reduce, how much, and we can get the data. Normally, the straight line is 180 degrees, we all know. This is showing about 175 after reduction, which is, but it is easy. There is enough for me to place the intramedullary nail. Now, coming into foot traumas, yeah, previously they neglected the field of orthopedics because foot was not that concentrated upon, but people want better function now, so we do a better anatomy. We use the correction. This is the talus fracture being fixed and showing accurate reconstruction of the angles. You don't have to bother about the angles. That is for the orthopedic surgeons, basically to show how we do with that. Simulators are mostly used, as the previous speakers have spoken, mostly used for either performing a virtual surgery before we actually go into the surgery, or for the young surgeon who has to learn the tricks of the trade and he wants to operate on a virtual model, we are using. And for me, it is mostly my orthoplastic surgeon. I want to get my range of motion of that particular implant, either in the knee or the hip. I use most commonly for this range of motion simulators. And this is one condition which was previously not diagnosed before the era of computer. For example, my patient comes with a pain only in the hip, only on walking, but on sitting, he has no pain. So this, when we take an X-ray, it is normal. When we take an MRI, it doesn't show much. I don't know what to do. Then we found out, after 3D models, we found out this is a normal acetabulum socket with the head articulated in it. What happens in these patients is, we found out there is some sort of impingement. This was very difficult to diagnose previously with the conventional X-rays and even MRI alone. What happens? There is osteophyte in particular segment of the bone. that comes and obstructs whenever the patient moves in a particular way, either if he wants to stand or from sitting position to standing, that comes in the way. So that particular movement, patient gets pain. This is either the problem in the socket or it can problem in the head of the bone. It is very difficult to diagnose by conventional X-rays. So what we do, once we generate a 3D motion in actual kinematics in the motion, for example, here, when the patient is sitting, the hip is at right over him. It is showing the red marking where it is impinging. So that is the cause for his pain. Whereas when the patient is standing, the impinging part has moved away. So he will not have, when this patient will not have pain in walking and running, but he will have pain mainly on sitting. High flexion, it will have pain. So this type of accurate data we can acquire. Then what do we do? So the impingement is only between, this is acetabulum showing the various clock angles, 12 degrees. The impingement is between 11 to 2 degrees here, 11 o'clock to 2 o'clock position. So I'm getting accurate data. So I have to just put a scope and remove this part of the bone which is causing the impingement. And after studying the we go through the range of motion, which is the hip is freely moving now. So this is the usage of computer generated models for diagnosing these type of rare conditions. And augmented reality is nothing but a combination of real world data to the computer generated data, where the surgeon can actually overlap the virtual model which is being generated onto the surgical field. So it is great, gives me better. Once I put my instruments, it gives me where I am in the bone without having to open up much. So augmented reality is a big role in navigation. Then pedography means it is pertaining to the foot. Pedos means it is foot. We receive lot type of flat feet, and people come, young patients come, I am not able to join army because of flat feet, rocker bottom feet, club foot, all these foot deformities we come across as orthopedic surgeons. And previously we used to do only with X-ray and CT, but now with advent of this 3D models, what we do, this is a system where we... Hello, I am receiving some crosstalk.
Sorry, sir. 1 second, sir.
Am I audible?
Yes, sir. You're audible. It's just 1 second.
Yeah, I am receiving some crosstalk, so I'm not able to. Okay. Shall I proceed?
Yes, please, sir.
Okay. This is the instrument which we use on the table. The sensors are mounted on the foot plate, and we mechanically press the foot on this foot plate. So where the computer then gives me what are the pressure points for this particular patient, whether he has a flat. Madam, I am still receiving some crosstalks, madam. I don't know. It's I'm using earphones, so it is more disturbing. So this.
I put everyone on mute, sir. You can continue now, sir.
Yeah, thank you. See, this is the foot model which is generated, and I can give a corrective insole, or during per-op surgery, I can see the pressure points where still I have to correct all these data, which is previously it was not documented, but now we are able to document. And the engineering importance, lot of things have been spoken about patient-specific implants based on the preoperative CT data. CT data has good bone contrast, so we can get actual implant designs for this particular patient. For example, here is a knee replacement. I have put a particular jig. This jig has been generated on the 3D printing by the engineers. And for this particular patient, through minimally invasive, I just have to fit the jig, and this is a soft capture where I have to cut the bone. So I don't have to bother about how much is I'm going to cut, how much is the orientation, because the jig is for this particular patient. This is an advantage when there are certain conditions where I cannot use a conventional jig, like extra-articular deformities or certain bone tumor conditions or post-traumatic conditions where the conventional jig may not work for these patients. And not everything is so green-eyed. We have certain pitfalls. One is the loss of, because we are using optical trackers, there should be unobstructed view between the optical sensor and the tracking tools. So the surgeon cannot move around much, or his assistant cannot move around much. We have to have an unobstructed view. And next is tool decalibration. What do you mean by that is the geometric data of the track tool does not match the actual geometry. This is more of a surgery engineering term that can happen. And navigation image inaccuracy can happen when there is a mismatch between the displaced images and the intraoperative pictures. Commonly, it is because of not taking time in registration errors. We have to take time in giving acute registration of the bony landmarks of that particular patient to the computer. And a brief about robotic surgeries. It is evolution in progress. Basically, the patient is on table and the surgeon sits in a separate console, or he can manipulate the robotic arm on the patient. This is commonly used in telesurgeries. And this is a console, surgical console, the surgeon's hands, and you get a 3D visualization of the operative area. And the surgeon hand replicates the C-arm, the robotic arm replicates the surgeon's arm, and the minute degree of adjustment in the 3D can be done. But mostly we are using in orthopedics is we are using as a burr for in the knee replacement procedures. Not in autonomous mode, but in a haptic mode where the surgeon controls the burr and starts drilling. Now, these are the clinical scenarios where I have used the computer assistance, where we cannot use a conventional surgery for these patients. For example, this is a patient who has a childhood injury, fracture. The plate has been fixed many years, almost 20 years back. And see the axis, mechanical axis, center of the hip, wide away from the knee. Here I have to do a knee placement. Previously, we have to correct this bone. We have to make it straight. Then only I can use a conventional jig. Whereas with computer navigation, I can bypass this. I can change my prosthesis orientation into a more valgus, where I change the process into a more valgus. And what I am getting, I restore the mechanical axis. You can see that after the joint is replaced, you can place the center mechanical axis of this patient. Whereas previously I had to cut this, and to use a conventional jigs are intramedullary. I had to put the jig into the medullary canal to assess what is my size. But with navigation, I can get away without doing anything for this. So this is the advantage. Next, this is a revision scenario of the hip, where you can see the normal hip on the left side. The process is migrated high up in the pelvis and loosening of the implants. And this is the actual head where it should have been. And the 3D generated model showing the extensive bone loss, no socket at all. So how do I fix this head? So this is a 3D generated image model where we are making a conventional prosthesis for this particular patient, and where I have to fill the bone, where I have to fit the screws, everything is generated, and the 3D printing is done. And once the model is generated, we actually fit into the patient, showing a good restoration. The head was high up here. You can see here, it has been reconstructed into its anatomical place along with a lot of bone grafts, so that this patient has got a functional hip. This is the importance of ligament balancing in the knee. See, this implant is accurately fitted, but this has failed in 6-7 months. The primary knee has failed because of the surgeon has failed to balance the knee. The knee ligaments are wobbly. The knee has started wobbling, and see where again the mechanical axis is passing. It is passing inside. So in these revision scenarios, it is better that I use a computer generated model and balance the knee perioperatively accurately, so that I don't have to fail again. And whatever, see, the implants you may use, the best of the implants, best of the metallurgy, but if your knee ligaments are not balanced properly, it is going to fail in the long run. So here you can see I don't know whether you are able to see the extension gap, flexion back there, which is matching. Extension means in full straight knee. Flexion is about 90 degree of flexion. This gap balancing has to be done accurately. That is you can see the parallelism between the two bones. That has to be maintained in extension as well as in flexion. Then only I'll get a good balance of the knee, ligament balance of the knee. This is the post-operative X-ray of the patient, where I use different processes designed, where medullary augments have been used. And you can see the restoration of the axis now, passing through the knee, which was not there preoperatively. And this is a pelvic tumor. There is a sarcoma of the pelvis around the hip joint. What has happened here is for resecting this, since being a malignant bone, after the chemotherapy, we have to resect this much of area. And we are beautifully seeing a reconstructed model, but we have to remember the blood vessels, the spinal nerves, and the pelvic organs, the uterus, bladder, everything falls here. So it is a major reconstructive surgery where we plan. And then this is a bone model, 3D generated bone model, which I have to give the surgeons for giving me a bone model, 3D reconstructed bone model for this patient. And I can hold only in the normal bone, where I have to place my screws. Based on that, we generate a model. And this is the model which is going to be implants, customized implant which has been made. This is made with basically either tantalum or titanium base and highly coated, porous coated hydroxyapatite, so that it allows bone ingrowth in the long run. This is showing the tumor resection and the socket of the hip, which along with the tumor, it has been removed. And now post-operatively, we have implanted this and reconstructed this. Previously, this was not possible. People landed up in hindquarter amputation of the lower limb, because being a malignant cancer. But now we are able to save the limb of these patients. What is the take-home message? See, we have to involve, the surgeon has to involve preoperatively. What all is possible is a 3D reconstructive one, which you have discussed, virtual operation simulated models. Perioperatively, I get my navigations and I'm able to place my implants in a more accurate fashion, which gives the patient longevity in the surgery and accurately reduce intra-articular fractures for better joint mobility, and in ligament reconstruction for the sports person to go back to his functional level of sports. And the post-operatively, as the engineering friends have discussed, finite element analysis can be, because all these data are stored for every joint, and we get a final data where we can present papers or compare with other colleagues. And this is the area where engineers and the surgeons have to work together, not only the biomedical engineers, the important metallurgy, what type of metal has to be used, and what specific instruments, as I showed you in procedure, where we can get a customized implant for a particular patient, and customized implants for a processes designed for hip and knee, and we can give better results for the patient with where my joint is going to function in the long run without any revision. And finally, a food for thought. We all know from physics, this Young's modulus, stress strain curve, everything for metallurgy. Metals, we expect the metals to behave like that. But unfortunately, for bone, doesn't follow Young's law. It follows what is called Wolff's law, where bone grows along the line of stress. So bone is a living tissue, which we cannot forget, and which undergoes constant remodeling. In our lifetime, every bone is undergoing constant, particularly in the lower limbs, where it is a weight-bearing bone. You can see the same bone, this is a femur thigh bone. The same bone, when it is loaded, when we are weight-bearing, walking, running, there is a compressive side to it, and there is a tensile side to it. So this is the problem where a rigid implant we may not fit the bone. That is why in trauma surgeries, even when we fix the fractures or anything, there is a failure in certain conditions. The bone doesn't unite. Whatever rigid metal you are going to use is going to fail. That is called implant failure. More than implant breakage, the bone fails if the implant doesn't unite. So these are my references. And thank you very much. I'll be happy to answer any questions if participants have.
Thank you so much, sir. We have few queries, sir. So the first one is, in knee operation, what is the material used in knee implant joint?
Yeah, we use the alloy of titanium, aluminum, and vanadium at present. And this is a commonly used because this alloy is bioinert and biocompatible, and it can be cemented in a better way. And there are oxidized zirconium implants, which is called the oxinium knees, which are also being tried in young rheumatoid patients, because young patients, we come at 35, 40 with rheumatoid, particularly in a female. We have to think of next 20 to 25 years. So we use oxidized metal also. Yeah. Any other questions?
Yes, sir. Thank you, sir. So how could we know if the implant is infected?
Oh, this is, see, the patient's well-fitted implant comes with, initially he has a pain-free period, comes with pain and fever or with warmth in the knee. Clinical examination also will reveal warmth in the knee, and he is not able to, the moment he is walking, he comes with pain. Unexplained pain in a well-fitted implant in the x-rays, the suspicion is infection. So it can be yearly, within about 4 weeks of implantation, or it can be delayed after about 6 weeks, or it can be late after 2 years. So depending upon the stage of presentation, we have to assess. In the initial stages, x-rays will be normal. We can only say if the patient has pre-existing condition like diabetes or a chronic lung infection, we have to suspect. And not only that, we do the biomedical markers like the CRP and other leukostrace test, all these, whether we are correlating. In the early period, we just have to save the implant by going into and washing the knee, we call debridement, and try to save the implant. In the late stages, when the patient presents with gross loosening and everything, we have to do revision, either staged or in a single stage, we do revisions, depending upon the stage of presentation. Basically, infection we diagnose by the presence of pain in a well-fixed implant and correlating with the biomedical markers.
Thank you, sir. Dr. Ram Prasad has one question, sir. Is there any drug-eluting implant?
See, presently we are actually in the implant. We don't do mix the drugs in the implant. Why? Because the processing has high temperatures. The temperature processing is there, where the implant is the drugs. When we give it to the implant, it will not act because of the high temperature. What we are doing is we are mixing in the cement, where we cement is bone cement we use, where it is a hydroxyapatite, where we mix either the thermoplastic antibiotics like tobramycin, gentamicin, or vancomycin. These are the antibiotics which are thermostable. So mix it with the bone cement and we are using. That is the way we use, not in the direct implant, because it will not be, because we sterilize these implants at high temperatures. So that is why we use it along with during the surgery, we use it along with the cement.
Thank you so much, sir. Do we have any other query? No, sir. So thank you so much, sir. We are grateful for the time and effort you took to share your thoughts and experience with us, sir. Thank you so much.
Thank you so much. Thank you.
Dear participants, so let's find up the morning session and we'll meet at 1:30 for our last session. Thank you. Welcome back, participants. So last session for today is on fabrication of nanoscale entities and peptide scaffolds for drug delivery, cutting the project cost using machine learning approaches by Dr. Surajit Debnath. Dr. Surjit Devnath is the head, Department of Medical Laboratory Technology, Women's Polytechnic, Tripura, with more than 30 years of experience in biomedical research. Over to you, sir.
Okay. So could you tell me what are the setting of the participants? Most of them are from biomedical department, or it is an interdisciplinary audience?
So it's an interdisciplinary audience. The doctors are also there.
Great. Okay then. So I'll share. Let me first do apology because of due to some kind of compatibility issue. I'll be sharing my this thing from a different kind of device that usually you are accustomed to in this kind of session, but I'll make it sure that it doesn't make any difference for your overall this thing, what do you call as experience. So please tell me whether it is visible to you.
Yes, sir, it's visible, sir.
Great. So what exactly we are talking about is the fabrication of nanoscale entities and peptide scaffolds. So in existing technology, peptide scaffolds are there, which are having multiple biomedical use. So usually in scaffolds, what happens is various kinds of peptides are being used. For example, the most frequent one which is being used for scaffolds are silk proteins from various kinds of silkworm, but there is a problem in that they are physicochemical we have not recently, for a couple of years, we have identified some specific small molecular weight peptides from various organisms, and then we were able to do the scaffolding in a simulated way, and we have understood that if we make a scaffold out of this kind of bioactive peptides, which are from microbial cultures, so there is an inherent anti-pathogenic activity already built into it. So what happens is the scaffold itself becomes by default anti-pathogenic, and therefore we expect that the activity of the scaffold and its utility would be much more. Anyway, so let us discuss about these aspects. So when we talk about nanoscale entities, we shall be essentially talking about that nanotechnology encompasses the understanding and control of matter at a dimension between 1 to 100 nanometers. At those dimensions, what happens is, since the dimension is very typical, these entities acquire a different kind of property altogether. So these are the nanopeptide we have isolated, and when we made a scaffold out of it, the scaffold itself, it is a tripeptide scaffold. This scaffold itself was within the nano range. So what happens is the peptides are already anti-pathogenic. Now the scaffolds are within the nano range, and therefore we expect that that this kind of design of scaffolding would have much more practical applicability. So rest of the other things are quite well known to all. At those dimensions, materials may acquire unusual physical, chemical, and biological properties and functions that are remarkably different from those observed at the macro level. So this is a known fact, and we are harnessing nanotechnology in a great way due to this kind of things. Now, this is a standard protocol. How do we establish the nano entity or the entity within the nano range? So what happens is there are two approaches in order to make up these nano entities. One is a bottom-up approach, and another is the top-down approach. Now, in bottom-up approach, what happens is we start from the scratch, and subsequently we build up something. For example, here if you see, In bottom-up approach, there are chemical synthesis, then self-assembly, then positional assembly. So we are talking about the units or subunits which we'll do through chemical synthesis, self-assembly, and things like that. Subsequently, there will be particles and molecules which would have different kinds of use altogether. So in our case, what we had is we had the particles and molecules which are nothing but the naturally occurring low molecular weight peptides. Okay. So here, what was our approach? We are already having a naturally occurring low molecular weight peptide or synthetic peptides. Now, in our case, we have isolated these peptides in pure form, and we have reported this phenomenon also. So subsequently, we had induced assembly, induced self-assembly, and subsequently we have observed the biomedical applications to it. So in our approach, it was a completely bottom-up approach. We'll discuss these things later once again. So subsequently, what happens is what are the direct applicability in terms of drug engineering and pharmaceuticals for these peptide-based nano entities? Let us briefly discuss it. So the nanomaterials for biomedical applications, which are having multiple usage according to the reports published in Molecules in 2021. But this is also true for nanopeptides. That means peptide-based nanoparticles, which are either could be the applications can be in diagnostics, then it could be in therapy, and then it could also be in drug delivery. So this is very interesting here. So we are not talking about a typical drug delivery here, which we will discuss later on. So here what happens is, as you can see here, for drug delivery aspects, there is this is used for medication delivery, then gene delivery. Okay, and in terms of therapy, if we see, the major three therapies are antibacterial therapy, then cancer therapy, and then regenerative medicine. So nanomaterials, in terms of therapy, there can be mainly three usage: antibacterial agents, which can act as an antibacterial agent, then for cancer therapy, and subsequently for regenerative medicine. So these are well-known aspects. But here, when we are talking about nanopeptides, what happens is there is a combination of properties. This is very interesting to see that when we make a scaffold out of peptides, which are already having some bioactivity, so there is a amalgamation of more than one property. So how do we do this? As I have said, that these peptides are already antibacterial agents, and they can be used in wound dressing and regenerative medicine as well. So what happens is there are two things happens all together. At the same time, the scaffolds are also used in drug delivery. So you are delivering a drug within a scaffold which is already antibacterial, and at the same time which is also having some regenerative properties. So what happens is ultimately there is a combination of more than one property which is already inbuilt to it. So we are far ahead. We have not reached that goal to make it a practical utility, but we anticipate that in near future our lab will get sufficient funding, and subsequently we can move ahead with this. So one more very interesting thing which is which must have come across to all of your attention is the field of theranostics. So what happens is when we are making a combo of therapeutics as well as diagnostics in the same entity, so we'll be talking about theranostics. Just one second. So this theranostics is also a very challenging aspect because what happens is the therapeutics as well as the diagnostics are coupled hand in hand. Now there are a couple of very interesting these things for this examples. For example, if you are having a monoclonal antibody which is having a particular fluorescent tag. Now this fluorescent tag is such that it identifies a particular tissue where a particular cancer antigen has been expressed. Now at the same time, it is also conjugated to a particular kind of growth factor or an inhibitor to it, which will inhibit the growth of the cancerous cell. So this is how a theranostic approach is there. And there are possibilities that within nano range, theranostic approaches can also be fruitful. Subsequently, if we go, this is a very interesting study which was been published by the Cavendish lab of University of Cambridge. So what has happened is the peptide entities in nano assembly, they can bring about a lot more that we have already have. For example, it can produce artificial membranes. Then subsequently, it can also lead to biomineralization and hybrid materials. Then 3D scaffold. Now this 3D scaffold is very, very interesting and is many labs in India as well have done excellent work where a scaffold has been made and then a particular kind of cell has been
Sir, you're on mute, sir.
So what happens is in this, what happens is this 3D scaffold once you make out of sericin or other proteins, and then you isolate a kind of cell, a specific kind of progenitor cell, which you initiate its germination, and ultimately what you get is a artificial tissue. So if you are using an osteoclast and osteoblast type of cells, you get a cartilage. Then if you have the potential to develop the pancreatic cells, then you ultimately get into a artificial pancreas. The potential is huge. So this is also very interesting part where nanopeptide based scaffolds can be used. Then there are fibrils. Now these fibrils can be used for many different purposes. As you can see, these are fibrils made up of small units, and you can initiate the polymerization of the fibrils as well as you can also initiate the depolymerization. So it acts like the natural phenomenon where the spindle fibers are generated and regenerated through which the chromosomes are moved from one side to the another during various stages of cell division. So there are possibilities of many such things. For example, nano robots. Now, when we are talking about these kind of things, what exactly the principle behind those? It is nothing but say this kind of thing only, where polymerization and depolymerization is regulated, and therefore you get by using cellular energy, you get some kind of mechanical movement. So these are all different aspects to it. I hope it is completely visible. It's a path-breaking study. Now, this is again, I would like to focus on, which will be timely as well. Now, this is the lab which during the 2012 for the first time proposed that in order to tackle coronavirus, at that point of time it was not COVID-19 or SARS-CoV-2, it was SARS-CoV-1, severe acute respiratory syndrome, coronavirus 1 it was. And this is the lab which proposed that there is a urgent need to make a nanopeptide based vaccine against COVID-19. So if at that point of time we would have been much more cautious, today's pandemic would have been may not have been possible. Anyway, there are different aspects to it. And we have taken prior permission before using these photographs and the discussions. Now, what is the need of these kinds of things? Now, the main reason behind this kind of adventures are more or less to going towards the precision medicine. Now, in precision medicine, what happens is a single drug will not be acting on everybody. a particular drug will be used for a particular reason or for a particular person. So if you see, there was a general pill. This pill was useful for a particular group of patients, but subsequently it was of no use for a other group of patients. So therefore, there is a desperate need of a custom-made medicine or a precision medicine for each and every person. There will be a specific type of medicine which will be delivered to the person, and subsequently everybody will have sufficient efficacy and he'll get rid of the disease. So this is the need, and in order to make it a possibility, there are a need that different persons come together of different backgrounds of biomedical sciences, chemistry, computer science, and so on. One more very important thing that I would like to focus on is the computer science has brought about a very large change. And the theme of this particular FDP is also this. Now we in science and study, we have also understood that computational simulation will be great in order to reduce the number of false positives and false negatives. So what happens is, if we are starting with 10 small peptides and trying different methods in order to make a scaffold, so if we are already having a simulation which says that, okay, if you go like this, your scaffolding will be much more stable. So what will happen is, we need not to invest a lot of reagents, because in wet lab experiments, a lot of costly reagents are there. So here there is also a mechanism which has been reported by Gupta et al. In bioengineering and biotechnology recently. So what are the different pathways through which the nano-engineered medicines can be delivered? So the first one, as everybody knows, the nanoparticles will be entered into the system through phagocytosis, and it will enter into the phagosome and subsequently delivered to a particular target. So there are clathrin coated endocytosis, as you know. The clathrin coated piths are there, which will usually useful for internalization of various kinds of cholesterol. So if your nanopeptide is coated with a particular kind of cholesterol, you can internalize this. So there are different methods. For example, if there is a receptor bound thing, it can also be internalized in a particular tissue, and then the activity will be delivered. So this is how different aspects are there, different forms of nanostructures, as you can see. So we are not discussing it in much more detail. We'll have a video in order to make it much shorter. So there are the other the scaffolding thing. So if you please look at it, you will see that the application of self-assembled peptide they are speaking. So self-assembled peptide is the thing which will form a scaffold all by itself. Otherwise, if it is non-self scaffolding also, we can induce scaffolding by very minimal cost. I mean, it is not a big deal to induce scaffolding. So what is the use? So one is in vitro biomimetic action, a particular, for example, what exactly pancreas does. So pancreas releases a hormone so that glucose metabolism can be easy. So if we entrap insulin in some way, or insulin producing cells in an entrapment medium, and then place it into the organism, the person or the patient, what will happen? So it will also release insulin the same way it does. So these are the different aspects to it. So here is again one more. There is an engineered nanoparticle which has been projected into the blood vessel. Now this blood vessel will carry the nanoparticle to the cancerous cell, and subsequently the cancerous cell will die. So this is also reported by Gupta et al. So these are the different aspects to it. So we shall see a video now. I'd request our coordinator to please run the video.
Second, sir.
Yes. So here I would also like to say that the post-lunch sessions are very challenging for the presenter as well, because most of the people will feel dizzy, and therefore it is a desperate attempt that nobody, at least those who are there. Now this video has been produced by Monash University.
Sir, is it visible, sir?
Yes. You just mute it and then play it. Yes. So it is highly relevant to our this thing, that what exactly happens. in precision medicine, and why you are interested in it. So this is a fluorescent microscope where different kinds of cells are observed. Now those who have been tagged by a specific fluorescent tag will be seen with a particular color under UV ray. So if you look at it, okay, I'll make it like this only. It will be much more good. So if you see here, there are two major types of nucleus. One is pink color, and some cells are there which are having blue color. Now these blue color cells are those cells where there must have been something wrong. So these are the cancerous cells, and now we are making a particular nano drug which will be delivered to this particular cell only. Now here you see there is a receptor mediated endocytosis. The receptors are coming together. The drug is designed in such a way that it will only come close to those kind of cells where there is a cancer. Now after entering into the cell, the clathrin coated pits are covering it. Now this is a vehicle kind of thing where from the surface, cell surface, it will enter into the internal sites. Now this vehicle is also such that it will not bind to, see here, it is bypassing Golgi. Now this is the Golgi body. It is also bypassing endoplasmic reticulum, and it is getting closer to where? To the nucleus, because it is programmed in such a way. So after coming close to the nucleus, what will happen? It will once again get merged, and the drug will be delivered internally to the nucleus after transporting through the nuclear membrane, either through the pore or through a different other mechanism. So what will happen is now the drug has been internalized, and now it is the right time to initiate the drug action. Now when the drug action has been induced, now here you see the cell is undergoing necrosis, or it can also initiate a kind of self-destructive pathway, which will ultimately kill the cell through many different pathways that we are already having. Now this is the general purpose. Okay, thank you, madam. Now I shall go back to my presentation all over again. Just 1 second. Just okay. Now this is the same study from the same lab, where we can show here that just hold on. Okay, where we can show that the scaffold is efficiency of the cell growth, and accordingly you can change that is the permutation combination, that which kind of ionic this thing is needed, how much carbon dioxide concentration is needed, so on and so forth. So you can do this. So there is a scaffolding thing that I wanted to do with a worksheet anyway. So here these are the very good examples of it, that after using a peptide based nano scaffold, the wound healing of a particular site of a cartilage was been excellent. Now this study was been reported by Chen et al. In SES Nano, I think, SES Applied Materials and Interfaces. Excellent study they have made, where they have individually shown that in a peptide based matrix, the growth of the osteoclast and osteocyte, or chondrocytes more specifically, will be much more. So if the chondrocyte growth is more and you can track the growth, it indicates that your strategy is good. So but here there is a difficulty. I'll show you in the next slide. So what happens is, since you are doing a lot of kind of in vitro thing in the tissue itself, there are possibility that you end up with a substantial infection of any kind. It could be mycoplasma, it could be viruses, bacteria, and so on and so forth. So there is an inbuilt threat that whatever do you do during this experimentation session, there are possibility that there will be subsequent risk of infection. Now the problem here is it is not a living tissue and you cannot inject an antibiotic to it. For example, when a surgeon is doing a surgery, he is he is very much cautious, but at the same time he knows that there is somebody who will rescue him if his patient end up with some kind of sepsis or some kind of thing. But here it is not possible. So your scaffold should be such that it is already entrapped with some kind of anti-infective thing, and subsequently you can do the rest of the experimentation. Now here we are showing you the type of scaffolding, peptide scaffolding. So as you can see here, we need a particular kind of pattern in the peptide. So here if you see, just 1 second, give me 5 minutes. So here if you see, there is a particular pattern in the peptides, okay? In the atomic level structure, if you see, there are parallel beta sheets, okay? So what does it mean? It means that in order to make a successful scaffold in the peptide itself, there should be some kind of regularity in the structure. Secondary and tertiary motifs should be there, and subsequently there are possibility that you end up with a successful scaffold. So this is one point. The image is from the Cavendish lab only, from University of Cambridge. So this is very important point. Now these are the motivations behind what do you call is nano engineering. So what happens is there are inbuilt mechanism in the cell itself where there is a top down and bottom up approach. Okay? If you can remember in the second slide we have shown, most of you are already aware to it anyway. We can discuss these things with our teachers, with our students, because most of the participants are either teachers or high-level research scholars, so they'll interact with a lot of students in their further the course of action. Now what happens is this is a very old approach which is very much known to all of us. So what happens is in the cell itself there is a top-down and bottom-up approach, and we are just replicating it. For example, as I have given you the concept of spindle fiber formation, which is nothing but a bottom-up approach of nano scale fabrication. So similarly, we can do the fabrication at a nano scale, and there are possibility that very good results are there. So here again, there are self-assembly strategies. For example, self-assembled fibrils can be formed, which can act as nano robots. In coming future, as I have said, in coming 50 years, it will be precision medicine will be a norm. And the need of precision medicine is also very much clear after the case of the pandemic. So if you go to, if, all of us have come across this pandemic in a very significant way, and there is nobody who have escaped from its as all of us know that once you have taken both the vaccines, there are no escape from this, because every day there are new and new variants to this particular virus, and it is there, it is going to stay forever within human beings. So what are your plans? What human can do? Either you can fall prey to the virus, or you can do something so that there is a kind of precision medicine, because as you know that a single kind of vaccine is not effective for all the strains, and therefore it may happen that for all different strains needed different kinds of vaccines altogether. So these are the different issues that we can think about. So self-assembly, as you can see, peptide nanotubes. Now once the nanotube is formed, you can self-assemble the nanotube themselves, and it will make an array of peptide nanotubes, which can further go for some other purposes. Now these are the very high level of approaches. Now, if we want to see a ACS video which has been generated to make the student understand that how exactly peptide self-assembly can work. So it is not for the teachers, but we can definitely share in our class. Yes, the second video. Okay, now angiogenic peptides are what? Angiogenic peptides are those which are initiating formation of blood vessels. Angio means blood vessels. So what will happen is these are nanopeptides which will initiate blood vessel formation. Now these having different usage to it. Sometimes it can happen that if we know the pathway how angiogenesis takes place. For example, in a cancer, what happens is, madam, please pause for a second so that I can give an intro. So what happens is angiogenesis is a process in which metastasis takes place. For example, you are having a particular kind of cancer, which is a particular in a site specific cancer, benign cancer. You can cut through it and you will be okay. But sometimes what happens is due to various factors, it develops blood vessels and starts entering into other sites by means of various specific mechanisms. Now this is a peptide which can initiate formation of blood vessels. So if we know the pathway how exactly this angiogenesis takes place de novo, we shall must say de novo, because in the cancer if angiogenesis takes place, it will be de novo angiogenesis. And if we know the pathway well, it may happen that we can inhibit this process and a benign cancer will remain benign and you can operate through it. So that was the idea. Anyway, but it has been an excellent study. Madam, please start. So molecular self-assembly, there is a hydrophilic tail. As I have said that they are, and the bottom thing is hydrophobic. So there is a particular, and this is the angiogenic. Now, instead of angiogenic, it could be anything as per your usage, how exactly you are planning your study. It could be something else also. So this is how, as you can see, the pattern, as I have said, there will be a pattern because one site is hydrophilic and another is hydrophobic. There is a pattern, and here you see the antiparallel beta sheets are being made. So this is how the scaffolding can be done for peptides, and it can go on. Now here you can see there is a regulation also. At one site it is getting in and other site it is getting down. So this is a steady state approach. Now what is happening in a steady state approach? You can modulate its activity. So the scientists have done a lot of experimentation with this. So this is what we are going to this thing, that what exactly are the possibilities of it. So instead of angiogenic, it could be anything as per your wish, as per your requirement for your experiment. But for scaffolding, there should be a specific kind of property with the a specific. Oh, sorry. Coordinator,
Sorry,
madam.
Sorry, sir,
Please.
Yes, sir, kindly go ahead.
Now similar approach we have also done, and I'll share our experiment results. So here what is happening, we can trigger the folding. Okay, so what will happen is, for example, you are having a peptide which is suspended in the in a solvent, so you can induce scaffolding so that the arrangement will there will be a kind of like tautomeric shift somewhere, and then it will induce scaffolding. So the scaffolding can be induced either by ionic radiations, and then temperature, then some chemical treatment, osmotic shock. So many things are there. So ultimately what will happen, there will be ordered structure within the nano range, which will have greater usage in terms of biomedical applications. So these are different patterns through which peptide scaffolds are possible. These are very high level study where they have done an excellent work, but we have not reached that. But within our limits, we have done scaffolding within 3 nanopeptides. We shall discuss these results as well. So what happens is, whenever we are talking about a peptide based therapy, these are the properties that should be there. So there should be low antigenicity. If you are delivering a therapy inside in vivo, there should be minimum antigenic. If it is highly antigenic, what will happen? It will end up with no function to it. Then subsequently there will be biocompatibility issue, biodegradability issue, then permeability on surfaces. For example, there is a blood-brain barrier. There are so many Lipinski rule is there which should be followed. So many different aspects to it. So before finalizing a kind of peptide you are working on, so many aspects to it should be there. Now here what is happening is, for example, you have identified a kind of peptide which is very good, but the problem is there are no bioactivity. For example, if it is highly prone to antimicrobial toxins and all, microbial toxins and all, your work may be lost in nature. So what will happen? We have identified a peptide which is inbuilt anti-pathogenic, and therefore there is a desired part of it. The desired part is enhanced anti-infective and pathogen control. So in our peptide, we have seen that it is anti-pathogenic, and therefore an advantage is there with it. So other than all these properties, if there are some added benefits to it, it is a good peptide with which you can start working on. Subsequently, here is very important. So it has been seen that in peptide based scaffolds that you are trying to use as a drug delivery mechanism or for some other usage also, the pathogen control is challenging, as I have already said. So in order to induce pathogen control, what are the common strategies are to incorporate curcumin and some other biomolecule entrapped in the scaffold, so that it becomes anti-pathogenic. So the many studies has been reported by using 2020. Recently, they have used a smart nanomaterial based PCL electrospun nanofiber, which is and they have embedded silver nanoparticles as well to make your scaffold anti-pathogenic. So there has been many study where external source should be used so that it becomes anti-pathogenic. But here in our case, because it is already anti-pathogenic in nature, and if we make a scaffold out of it, it will be highly successful. So, and here also you see in this study in ACS applied biomaterials only, here you see the scientist had made a scaffold and then they are trying to establish its anti-pathogenic effect. If you can see in the part C, they have done a agar-well diffusion assay. Okay, a simple assay that we usually do in our lab in order to identify what is the potential of anti-pathogenic potential of a particular thing. So they have done an experiment on the same material itself. So what we are trying to say is the controlling of pathogenesis is a very big challenge. But in our case, it is already inbuilt to it. That is the peptide that we have isolated is already anti-pathogenic in nature, which we have confirmed through various modes, and then we are trying to make a scaffold out of it. Now this is the result we published in 2015, I think 2017, where we have identified a peptide which was anti-pathogenic in nature, and then we tried to make into a scaffold. So in order to doing the scaffolding part, there has been several steps. We empathize that there is a desperate need that peptide-based scaffolds are a reality. Then we identified the problem, then ideated that what are the possible things that we can do in order to make make it a reality. Then we made a prototype and then subsequently tested it. But interestingly, I should say that from define to test, these 4 steps we did through simulations. So what has happened is we have reduced the cost of our wet lab experiment to a substantial way. And therefore, within a limited budget also, we can move ahead with our plan. So it is just a sharing of my experience in while doing this, so that other researchers, even students, can think of this kind of things in order to do their high-end research. So what happens is, this was our study where from a kind of microbial source, we identified a protein. This protein was subsequently monitored, studied, and analyzed, and we found that it is a 9 amino acid based small peptide with very low molecular weight, and there is a huge scope that they are getting scaffolded, and it can make into a larger platform on which we can generate artificial tissue. We can even use it for drug delivery and so on and so forth. So what was the thing? This was the structure of the 9 amino acid based peptide, which has a potential to the ability to assemble into a nano dimension itself, and it is also thermodynamically stable. Now, when we are talking about stable, what does it we are essentially talking about? We are essentially talking about its shelf life. For example, you have isolated a protein, but the problem here is you need to preserve it always at minus 20 degrees centigrade. So what will happen whenever you deliver it in vivo? There are chances that you end up with nothing. So this is also the case of today's vaccines. For example, the vaccines are there, but its stability is such that you need to preserve it in a certain way. So therefore, what happens is the ultimate cost of a vaccine increases to a subsequent or a substantial aspect. So our approach was also to see whether stability is there or not. Now, this is the dimensions of the singular peptide, which is within the nanoscale. Then when we made into a dipeptide, okay, now when we made into a dipeptide, I expected to do a hands-on so that you also can see how exactly the peptides look like. But due to some limitations, I'm not able to do it. But I planned this session in such a way that there will be a small hands-on at least. Anyway, so this is the dipeptide where the duplex peptide, 2 peptides are assembled side by side. The ultimate dimension is also within nanoscale range. And when we made into a tripeptide, 3 peptide molecules side by side, this also within nanoscale range. If you can see, the largest axis is 20.99 angstrom, and here the small axis is 17.4 angstrom. So this is well within 100 nanometer. And so there are scope that we end up with a scaffold which is within nanoscale range, and therefore we expect a lot of activity within this, because we have seen already that if something is within nano range, there are possibility that it acquire substantially new chemical and physiological properties. So this is the energy landscape. So when initially the single peptide was there, we calculated its energy through GROMACS, which is a molecular simulation package. We usually call it molecular dynamics. So in this dynamics, we identified that there are an energy of up to minus 39 kilojoules per mole. Now, when we made into a dipeptide, to our surprise, we found that the energy has been reduced to minus 123 kilojoules per mole, and subsequently in a tripeptide, it was much even more. So it ended up with minus 145 kilojoules per mole. So this is our initial study that the thermodynamic stability enhances, and therefore it can happen that the formation of the scaffold will be a spontaneous process once we start it. And this is the domain mobility. We did it Brownian dynamics to understand the mobility of different domains. So the bottom one is the singular peptide where high mobility can be seen. As you can see, the magnitude is very high. Subsequently, when we made into a dipeptide, it has been reduced to a great extent. And finally, in the tripeptide, there has been very great decrease in the overall mobility. This also indicates that the peptide assemblies will be stable. So I'd like to have the videos, the third video, madam, if we play. Okay, now this is the domain motion. If you can see, madam, please play. Yes. So here, this is the singular peptide. So what happens is when we make into the solvation box and start the simulation for like approximately 10 picoseconds, we see that most of the domains are lost. Okay. So therefore only the sum of the part of the peptide is seen. As you can see that the structure cannot be seen in a stable way. It is already broken into so many pieces because you are putting so much, you are putting a electric field, a dynamic field on the protein, and therefore the stress is so much so that the protein undergoes denaturation. Now this is the singular peptide. Now madam, if you please play the second video where we have simulated the dipeptide. Okay. Now, yes. Now, when we play the dipeptide, madam, now we have repeatedly take the snapshots and made into a video. So each and every snapshot was for highest for 100 picoseconds, and subsequently we made it into a video. Now here you, madam, please see. The audience, if you can see, the domains are clearly visible. So the alpha helix is visible, at the same time the loops are also visible, although it is getting distorted, but it is somehow stable. So what does it mean? It means that when we are assembling it, or there is a self assembly, there is a substantial increase in the stability of the protein. So the stability is good, the dimension is within nano range. Now these are the things that prompted us to go for the wet lab experiment. So thank you, madam. Now I'll go back to my share. Just hold on. Just 1 second. It will be okay. 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 This is again a peptide that we isolated from our lab and we made into a successful scaffold. Now its results are better. We have not made into a proper analysis that why the results are better, but here the results are better. I shall show you. The stability has increased to a very, very significant extent, and therefore, yeah. So excuse me, I shall once again rejoin. I think then it will be okay. Excuse me for a second. I shall rejoin.
Sir, is there any trouble, sir?
Sorry for the inconvenience. I'll. Am I audible, madam?
Yes, sir, you're audible, sir.
Okay. Thank you. So the idea behind this is to identify small peptides from natural sources, then subsequently characterize them, and then try to make a nano scaffold, and then the scaffold should be studied, and finally we shall explore the possibilities to grow cells on it, or to embed or to immobilize drugs, liposomes, vaccines, and so on and so forth, like the other people do. But here the advantage will be that the pathogen control will be an inbuilt feature, and since it will be within a nano range, it can happen that your bioavailability is much more. The pharmacokinetics and pharmacodynamics are much more favorable. In this way, this could be much more beneficial for patient care. So that was the idea. So I am very much sure that you have already gone through this kind of discussions, which will enhance people to do more valuable research. So this is the second peptide. We are about to publish it. Here you see the substantial increase in peptide 9B, we call it. It is 381.22 kilojoules per mole, which is very high from that of the singular peptide, if you can see. Now this was the singular peptide, which was stable, but not that. Here you see it was only 166, whereas the final peptide, the tripeptide, up to tripeptide assembly we can study. We will go ahead with much more, but we need more funding to do away with this kind of simulation, which require huge investment in terms of hardware as well as softwares. So this was the second peptide where there has been some changes in the domain stability. Now here what is happening is domain stability also is not an indicator of overall stability. It can also happen that there are some more activity which are embedded in those domains. So these are yet to be studied by our team. So okay, there was one more movie file that we have already analyzed. So this is, so while doing this kind of study, we came across that we needed some more tools that can be used. So for last 4 years we were working on this kind of project, and subsequently this last year we developed a patent out of it, which reads as system for rapid and low cost detection of mutations on proteins. So what happens is the proteins can be engineered by incorporating specific site directed mutagenesis on a particular amino acid. So it can enhance your stability of the protein. At the same time, it can induce certain feasibility so that it undergoes scaffolding in much more rapid way. So there are various aspects to it, and we are anticipating to monetize our patent in shortly in collaboration with some other labs, but we are in process to it. That was the thing we overall, this is the setup of the system that we developed, and subsequently this is the notification that we got recently from the Indian IP office, and we are trying to collaborate with established labs which are having very good simulation platforms as well as in vitro drug testing facilities, and we are open for collaborations. By saying so, I would like to conclude today's session, which was focused on the usage of peptide-based scaffolds and their applications. And I'll be happy if I can answer some of your queries.
Thank you so much, sir. Participants, do we have any queries?
So I'd like to this thing that thank you the coordinators for giving me the opportunity to interact in this platform. If there are some specific queries, I would have been very happy to answer them.
There's no queries as of now, sir.
Okay, okay.
Thank you so much, sir. Thanks for disseminating your brilliant work and research to us. It was an amazing session, sir. Thank you so much,
Thanks
sir.
a lot. Okay, okay. Thank you, madam.
Thank you so much for your patience listening. Let's wind up for today and we'll get back tomorrow morning. Thank you.